Hello students. Welcome to the YouTube channel, Physics Simplified. In this video, we will discuss the projectile motion down an inclined plane, and will find the expressions of various quantities associated with this motion. So, without any further delay, let's jump into the discussion. Let us consider a plane, inclined at an angle beta, with the horizontal, as shown in the figure. A projectile is fired from a point, say O, situated on the inclined plane. We draw a straight line, from the point of projection O, parallel to the horizontal. So, this angle is also beta according to the conception of alternate angles. Let us consider, the projectile is launched down the incline, with initial velocity u, making an angle alpha with the horizontal. The projectile strikes the inclined plane at point B. So, the distance OB represents the range of the projectile along the inclined plane. From the point of projection, we have dropped a perpendicular ON on the horizontal line. According to the figure, the angle made by vector u with the inclined plane is alpha plus beta. Considering the point O as the origin of a two-dimensional coordinate system, we consider the positive x-axis along the inclined plane and down the incline, while the positive y-axis is considered perpendicular to the inclined plane in the upward direction. We know that the acceleration due to gravity always acts vertically downward. Then, initial velocity u and acceleration due to gravity g can be resolved into two components each. One along the incline, and the other perpendicular to the incline. According to the concept of vector resolution, the component of the initial velocity down the incline is equal to u cos alpha plus beta, and component perpendicular to the inclined plane and upward is u sin alpha plus beta. Similarly, the component of acceleration down the incline is g sin beta, and that perpendicular to the plane and downward is equal to g cos beta. Before finding the x and y components of the initial velocity and acceleration with proper sign, let us make the current topic more familiar with our previous knowledge of projectile motion. To do this, first we rotate our new coordinate system, such that our new x and y axes look like this. This new temporary orientation will help us to determine the x and y components of initial velocity and acceleration with proper sign. The x component of the initial velocity is along the positive x-axis and is given by u suffix x equal to u cos alpha plus beta. The y component of the initial velocity is along the positive y-axis and is given by u suffix y equal to u sin alpha plus beta. The x component of acceleration is along the positive x-axis and hence is given by a suffix x equal to g sin beta, which will act as the acceleration for the motion along the x-axis. Finally, the y component of acceleration is along the negative y-axis and is given by a suffix y equal to minus g cos beta. This will act as the retardation for the motion along the y-axis, as it is against the y component of the initial velocity. So, we find that, unlike to the case of a projectile fired at an angle with the horizontal, here the x component of the velocity of the projectile will be accelerated. Let us now calculate the time of flight of the projectile down the incline. It is the time taken by the projectile to go from point O to point B down the inclined plane. During the time of flight of an oblique projectile, the net vertical displacement of the projectile becomes zero because the projectile returns back to the level of projection. If we denote the time of flight by capital letter T, then according to the figure, the projectile reaches point B in a time equal to capital T, and its net displacement along the y-axis is zero. The data along the y-axis available to us. Initial velocity along y-axis, u suffix y, is equal to u sin alpha plus beta. Acceleration along y-axis, a suffix y, is equal to minus g cos beta. Time is equal to capital letter T, and displacement along y-axis is equal to 0. From the second kinematic equation, we write y is equal to u suffix y times t plus half a suffix y times t squared. Substituting the given data and taking t common from the right-hand side of the equation, we get this equation. From this equation, we get two solutions of time of flight. One of them is t equal to 0. This is impossible because time of flight equal to 0 means the projectile is at the point of projection. So, the valid solution for the time of flight can be obtained from the equation u sin alpha plus beta minus half g cos beta times t is equal to 0. So, time of flight of a projectile down the incline is given by t equal to 2u sin alpha plus beta divided by g cos beta. Next, we will calculate the maximum height attained by the projectile while projected down the inclined plane. Maximum height of a projectile is that height to which it rises above the level of projection. So, in this case, it is the maximum height to which the projectile rises above the inclined plane while projected down the incline. Since, at the highest point, the vertical component of the velocity of a projectile is 0, hence, the y component of the velocity of the projectile is 0 at the highest point. Again, considering the data along the y-axis, we get initial velocity along y-axis, u suffix y, is equal to u sin alpha plus beta. Acceleration along y-axis, a suffix y, is equal to minus g cos beta. Final velocity, v suffix y, is equal to 0, and displacement along y-axis is equal to capital letter H, where we have considered h to be the maximum height attained by the projectile. From the third kinematic equation, we write v suffix y squared is equal to u suffix y squared plus 2a suffix y times y. Substituting the given data and simplifying, we get 2 g cos beta times h is equal to u squared sin squared alpha plus beta. So, the maximum height attained by the projectile fired down the incline is given by h equal to u squared sin squared alpha plus beta divided by 2 g cos beta. Next, we will calculate the range of the projectile down the incline. For a projectile fired down the incline, range is the distance covered by it along the inclined plane during the time of flight. According to the figure, it is given by OB. If we consider the motion of the same projectile along the horizontal, then during the time of flight, the projectile goes from point N prime to point B with uniform velocity because there is no acceleration in the horizontal direction in a projectile motion. Since the initial velocity vector of the projectile makes an angle alpha to the horizontal, hence, the component of the velocity of the projectile along the horizontal is u cos alpha. This remains constant. So, the covered horizontal distance by the projectile during the time of flight is given by n prime b is equal to u cos alpha times t. Substituting the expression of time of flight and simplifying, we get n prime b is equal to 2u squared sin alpha plus beta cos alpha divided by g cos beta. Now, from the right angle triangle OBN prime, we have cos beta is equal to n prime b divided by OB. Therefore, OB is equal to n prime b divided by cos beta. Substituting the expression of n prime b from the previous equation and simplifying, we obtain the range of the projectile down the incline, and it is given by capital R is equal to 2u squared sin alpha plus beta cos alpha divided by g cos squared beta. Finally, we will find the condition for range to be maximum down the incline. To do this, we need to find the angle of projection for maximum range. We have already calculated the expression of range of the projectile down the incline, given by this equation. Let us rearrange the equation in the following manner. From this equation we find that the fraction u squared divided by g cos squared beta is a constant at a given place for a given projectile motion down an inclined plane. But the term within the second bracket is a variable one, as it contains the angle alpha, which is created by the initial velocity with the horizontal. To find the condition for maximum range, we consider the trigonometric identity given by 2 sin A cos B is equal to sin A plus B plus sin A minus B. Making an analogy with this identity, we can rewrite the expression of the range as follows. Here we have considered alpha plus beta to be analogous to A and alpha to be analogous to B. Upon simplifying, we get R is equal to u squared divided by g cos squared beta times, within second bracket, sin 2 alpha plus beta plus sin beta. We mark this equation as number 1. Since u, g and beta are constants, so R will be maximum only when sin 2 alpha plus beta is a maximum. So, the angle 2 alpha plus beta must be equal to 90 degrees, that is, pi by 2, because sin gives maximum value at this angle. Therefore, alpha is equal to pi by 4 minus beta by 2. So, for this angle of projection, a projectile fired down the incline, the range along incline is a maximum. Let us now find the expression of the maximum range. Substituting this condition and rearranging, we get maximum range R max is equal to u squared divided by g into 1 minus sin squared beta times 1 plus sin beta. Further simplifying, we get the final expression of the maximum range of the projectile down the incline, and it is given by R max down the incline is equal to u squared divided by g times, within first bracket, 1 minus sin beta.